Great. Hi, everyone. My name is Talia. I'm a fourth-year PhD student at Maria Lagada's group. And today I'm going to present our work on identifying moments of change using the model we developed, TempoFormer, for mental health monitoring and identification of change over time. So to begin about motivation, dynamic representation learning plays a pivotal role in understanding the evolution of linguistic content, and it's very important in identifying change. So this signifies how important it is to have models that do not treat language as static. Here is an example of a timeline from the task of identifying moments of change in user posts. Initially, the user has a neutral stance in the orange boxes at the beginning, and over time, the behavior escalates. Therefore, we see that the context here provides very important information in identifying this change, which we might not necessarily be able to identify the progression and escalation in behavior if we didn't have the context. And apart from that, time is also important. So here we see that we have timestamp data because we can see in our models that it enhances the signal. And this is often overlooked in models. So we're going to address both contextual and temporally aware models here. So this is just an example. I'm going to go through the task of mood change identification today, but obviously such a model can be very helpful in other tasks such as change in conversation topic or change in public's opinion online. Just to address a bit about the motivation of our work, a lot of work that tries to address both the linguistic and the temporal dynamics at the same time lacks generalizability, so focuses only on one specific task. And a lot of the models, or most of the models, rely on pre-trained representations, so they do not fully leverage the transformer architecture and the attention mechanism. Or other models use recurrence, which can be slow and prone to overfitting. Therefore, we seek here to provide a unified, generalizable approach in creating contextualized dynamic representations. Lastly, in longitudinal modeling, temporality is generally overlooked or is trivially integrated using handcrafted features of time. So here we propose a solution that integrates temporal dynamics in the transformer with linguistic dynamics and is task agnostic. And here we're going to introduce TempoFormer for this. Just going through the specifics of this work, we wanted to showcase the generalizability of this work. So we tried 3 different data sets of diverse tasks and different temporal granularity. So starting from left, the first data set we tried is on Twitter conversations and identifying changes in the public's opinion over time. Then TalkLive data set is about mental health. So TalkLive is a peer-to-peer support network where people post about their behavior. Therefore, we can use their timelines to identify whether there has been a change in their behavior. And the last task is real human-to-human conversation, where we aim to identify major changes in the topic of conversation. And as I said, every task has a different temporal granularity, and we choose to formulate these tasks as a classification problem. So just to dive into the model, I'll try to give a general overview and take Q&A about the specifics later on. So as the input, we get timelines of user data and we form windows, and we call these streams. So given what we saw all the way before, this is a stream, for example, where we have the current utterance in green and then the previous context in orange and the timestamps as well. So this will be the input in the model and in a predefined window, and we initialize our model with the BERT architecture. The changes that we make is that we do keep the bottom 10 layers of BERT the same because we still want to capture the word level dynamics. So at this point, we just keep the same layers and fine tune them because it's still important to learn something in the token representations about the task and the specifics of the user's language. And we ignore time at this point. But what we do is we modify the top 2 layers, which I'm showcasing here, to capture the contextual and temporal dynamics. So in the 11th layer, we get inspired by long document modeling, which leverages a hierarchical approach. We call this part the stream level encoding part, where we aim to build stream context enhanced layers on top of post level representation. And the idea is to capture the stream dynamics altogether rather than having each word operating in isolation. So to achieve this, we first introduce position embedding to capture the position of each post, and this introduces a post ordering. And then we use another BERT layer that can propagate this position information that is quite trivial. And then what we do right here, which is part of the novelty of this work, is we introduce a temporal multi-head attention. So I'm going to talk in the next slide about reformulating the rotary multi-head attention to introduce temporality. Because in the typical transformer architecture, you have embeddings that capture the position, but not the time. So the idea here is to modify those to introduce temporality. And that's going to be explained in the next slide. We get the CLS tokens to interact with each other right here. And the idea is that these temporal context-aware tokens are fed back into BERT to enable the propagation of learned stream embeddings to the post level. So diving into the novelty on the temporal multi-head attention, I'm just gonna skim through it. What I want to show here is that we propose a novel variation to the rotary position embedding. So how the rotary position embedding works is what I'm showcasing here. Basically, you introduce a relative rotation between the positions of the token. So n is the position of one token relative to m of another token, and this applies for all tokens, obviously, to capture how far they are along in the sequence. And the further along they are, the less interaction they have. So what we introduce here is to rotate these positions, but instead of using the absolute position in the sentence, we use the temporal position of the streams. So that's the whole idea. I'm happy to answer any questions afterwards or engage in a conversation if you have further questions on that. But by doing this, we capture for each utterance in the sequence the dynamics, and we give less attention to things that are further away versus what is close by based on this mechanism. So lastly, we introduce a second layer of stream level positional encodings, and we feed that back to the last BERT layer. And this will make our tokens be context aware. So now the tokens saw from the interaction with the CLS tokens, they saw what happened in other utterances. So now they can learn representations that understand what happened in the whole stream. And by having CLS tokens that are stream aware, and therefore they contextualize the token level representation based on both the temporal and contextual dynamics. And we perform finally classification tasks. So we combine 2 items. One is the local here, the bottom, it's a bit overlap. Yeah, the bottom CLS is basically introducing information about the specific last utterance that didn't see the dynamics of all the stream, while the top one is aware of what happened to the stream. So by combining both of them, which what has been proven working in the literature, we can classify effectively whether we see a change in the user's behavior, a switch, an escalation, or no change. I'm going to quickly go through results. So here we compare models on the post level, so that see just the last post, and on the stream level, which see the whole stream. Obviously, TempoFormer is a stream level model. The takeaway from here, just right off, is that we managed to show in all the 3 tasks that there is state-of-the-art performance. And this is maybe out of battery. Oh, okay. Yeah, this is quite significant because each task has different temporal granularity. So the fact that we surpass the other baselines for all of them shows the generalizability of this work. And we perform better than the previous state of the art, which were RNN-based models. So that's very significant since it has been very hard to introduce a model that doesn't have recurrence as a state of the art. And just one more note on the results is that we decided to try LLM-based models. So on the post level, we see that performance is quite poor, and that aligns with literature that shows that temporal and sequential there are temporal and sequential limitations in LLMs. We can see that in some cases, for example, here, the models are doing worse than random, which is quite bad. We do see that when we try LLMs on the that see the stream, the whole stream, they do improve most of the times, not always. But there is no evidence that they do understand the dynamics of the stream. So there is a lot of work to be done there, and they quite fall behind compared to all the other stream level models significantly. So that's one of our main findings as well. Finally, just skimming through 2 last findings. So we tried to use this model as a foundation model for other architectures. So let's take what we have and put an RNN on top, LSTM on top, which is the state of the art. And we see that when we decide to do that for tasks that they do benefit a lot from recurrence, we do better than other state of the art on that. For example, in the social media task of identifying changes in aggregated opinion. So we can always beat these baselines, but most of the times TempoFormer on its own is enough to provide state of the art and balance both the stream dynamics and the contextual and temporal dynamics. And finally, we swap the BERT architecture with Roberta architecture, and we see even more improvements because obviously Roberta has been pre-trained for with more data. So the TempoFormer manages to propagate that improvement in the architecture even further. So you see how TempoFormer with Roberta is doing better as TempoFormer with BERT. So in conclusion, just to summarize, we introduced the first temporally aware transformer-based model called TempoFormer. We jointly model the contextual and temporal dynamics. We do that in a hierarchical fashion that is meaningful from words to post to timelines through different layers. Importantly, we reformulate the rotary temporal embeddings to measure the temporal distance, which can be used in other architectures if someone finds it of interest. And we provide a generalizable performance state of the art in 3 different tasks of different temporal granularity. And we show that our model is flexible to be used as a foundation architecture and adaptable to other transformer-based models. Thank you. Feel free to scan the codes to read more. Yeah, I'm happy to take any questions or speak afterwards. Yeah, let's see the question.
I just wanted to ask, this is probably a naive question.
You need a microphone. We had 2. What happened to the other one?
I was wondering whether you could distinguish between a change of topic in a conversation where people want to maintain the conversation
Mm.
and a change of topic constitutes disruption
Mm.
of the conversation, which we find a lot on the internet. Yes.
Yeah.
So, you know, if a troll comes along, if a troll comes along
Mm.
and simply changes the topic, meaning to disrupt the conversation, to stop the conversation, that's quite a different thing from, you know, changing the subject within a conversation, so to speak.
I think that actually the latter, which is changing the topic intentionally and diverging the conversation, would be even easier to do because the context also changes. So it's completely moving away from what has been said before. So the model should be able to identify that there is a significant change in the context and discussion topic. Therefore, I think with the right data, that can definitely be addressed. And these two tasks, they have similarities, but also with the right data, they can be easily differentiated. So I think that's possible.
Yeah, I still think there might be a difficulty over, you know, having a conversation that I'm having with my friend where I simply want to talk about something else that occurs to me, and having a troll come in and disrupt the conversation. I mean, that's just an interesting use case,
Yeah.
which there'd be a lot of interest in, I think.
Yeah. Thanks a lot. Yeah, that's a great recommendation.
It's a bit like a follow-up on the previous question. I just want to ask more on the data or the category of the changes that the model are capable of identifying. Is like in the data set, you already know like these are the type of changes that you are going to use this model to identify, or it's like theory driven that you have from like psychology literature that you know what type of changes that you're looking for.
Yeah, so yeah, right. The data are in a supervised fashion, so they are annotated, but not always annotated for the specific task of change. For example, for the first task, we reformulated the data to provide that. So for example, for the first task, the data were annotated to show if someone agrees or disagrees with the original topic. That's all. But in general, if the public opinion as a whole is evolving, we did a reformulation. So I think there are options where you can take something that is already annotated and reformulate it to identify change. So yes and no. Obviously, if you have the data already annotated, it's great. But
can I just also say that we did try a version where we didn't have a supervised method, so it was basically looking at similarities between the representations, and also so it was two different ways of doing it, and they didn't perform as well as this approach. But it's in, I think, that Adam's paper from 2022 that is referenced in Talia's work. So you could find more about the unsupervised methods that we used as well.
Yeah, my question was just about your data sets and how you access them. And I'm just wondering about the ethical issues of accessing social media posts, specifically around sort of mental health and peer support.
Yeah, great question. Yeah, I mean, we got ethical approval from board for Talk Live dataset. Is not, we do not release anything to do with the data or the models because we don't want to even think about the risk of leaking any private information through even the models. But yeah, so we don't put it out there. We have it internally after approval. But given that someone has this data, they can reproduce, or similar data, right? They can reproduce.
Yeah, so we had a license with Talk Life, who in their privacy agreement had sort of declared that data could be used for approved research. So we applied, and that's how it happened.
We have 3 minutes.
Hi, thank you, and really fine work. Just wanted to ask if among the things that you kind of modeled, do you think that the rope is essential for the success, or do you think that did you try like ablation study, like the model without rope?
Yeah. I mean, I did not put that slide. Don't know if I can hide it, but we did ablation with the rope, and actually, I think it's one of the central items of this model. I mean, the rope captures two things. One thing is the attention important, like the attention between the pause, so the contextual part without the temporal. Let's just remove the temporal aspect, and the second aspect is the temporal element. So we did ablations with both. Contextual relationship is the most important, so applying the attention on the context is very significant, and temporal dynamics are also significant but secondary, but they also give an extra boost in performance and signal. So it's quite central, and I think as an architecture on its own can be very useful in other settings too.